Just to introduce myself, so I'm Jamie Goggins. I'm a senior lecturer here in the university. I'm also involved in Engineers Ireland on the West Region Committee. The talk tonight is on marine renewable energy, state-of-the-art tools for developers. So we've three speakers, Reduan, Anna and Ed. So the three speakers three of them have recently defended their PhDs. We've been working in the MaREI Centre, which is the Centre for Marine and Renewable Energy. It's a national centre that does research on marine, but also research on renewable energy, both renewable energy at sea as well as on land as well. So the centre was set up just over 4 years ago, and our three speakers today are three of the first PhDs to come into the centre. So we're very proud to have the three of them graduating, all working in marine and renewable energy, all in different areas. So this evening is about them, I suppose, telling everybody outside of our group within the university what they have done in their PhDs. So we believe that there's very useful tools that have come out of the research projects. So Redo's going to start first. He's going to concentrate on the wave side of things, and in particular on wave resource assessment, and looking at the three different wave energy test sites in Ireland, and how a developer might go from one site to another. Then Anna will talk about the resources in terms of the tidal side of things, and then Ed will focus on the tidal turbine devices, and in particular the rotor blades for those devices. So we're going from the wave to the tidal in terms of resources, then to the device level then after that. So I think we'll skip the long introductions of introducing them. Their profiles are up online, and we'll get going. Okay, so if I ask Redo to start, he'll set the first presentation.
Hi everyone. So my name is Redu. I'll start off with numerical modeling investigations of the wave resource at Ireland wave energy test sites. So this is based on my PhD. So we'll start with introductions, and then wave characterizations, model development, detailed assessment, resource scalability, and finally conclusion. A bit of my introductions based on my previous background. So I used to work for HI, Water Environment, for 5 years. So my work involved global wave models, and then I also developed regional wave models, which is covers South China Sea, Bay of Bengal, and also Australia. And with that, I also involved in all local development models with different projects for local models. We normally do wave, hydrodynamics, mid-ocean, sediment, or mud transport, depending on the properties of the beach. And also on the environmental impact assessment, which is EIA. But today I will be talking about my PhD work, which is in Ireland for wave resource assessment, resource scalability, and also impact on the wave energy computer, which is called WAC arrays to the nearshore wave climate. So Ireland is located on the energetic wave zones, which is the wave power on the west coast of Ireland up to 70 kilowatt per meter. Therefore, this detailed assessment was required for resource characterizations and also variability, which is then important for WAC design and optimization. So there are three test sites in Ireland. On the west coast of Ireland, there are Galway Bay test sites, which is here, and then have the Atlantic Marine Energy test sites called UMAT, and also West Wave. And also, just focusing on my PhD, so we have 5 developments in my PhD, which is first is development of methodology for characterizations of operational and extreme wave conditions. And then with that, I developed a nested model at Galway Bay, West Wave, and UMAT. And then with that, we provide a detailed wave resource assessment, and then looking into the scale between their sites, and finally the investigations of the impacts of WAC at West Wave. So for the characterization methodology, so the scope for this project is actually looking into the characterizations of wave based on operational, high and extreme conditions, and that is based on percentage of wave occurrence. So for the operational conditions, there are events that actually fall from 0 to 90 percentile, and then for extreme they are above 99 percentile. So for oceanic condition, basically there are waves at the average conditions, and these waves are mostly occur the most. And then also these are important for device optimizations for energy capture. As for extreme conditions, they are important for device survivability. So just looking into the power assessment based on my first published paper at Galway Bay using wave rider data. So we conducted assessment based on 5 years period from 2009 to 2013 and calculate the wave power based on the wave height and wave power. So HS refers to significant wave height. So TE refers to energy wave period. TZ is zero crossing wave period. So since we don't have energy wave period data, so we use the ratio between wave height and wave periods from the published paper by Cahill, and with that we calculate the wave power. So based on the analysis, it shows that 2010 was the lowest, while 2013 was the highest. And also we have CODA data at Galway Bay, so we're also looking into the characteristics of wave height at Galway Bay as well compared to the wave rider. Then we're also looking into the wave occurrence based on wave height and also wave period. So by looking at this occurrence plot, you can see that the numbers now match with the colors. So that means so the highest occurrence occur under the operational conditions, while now the extreme is at the 99 percentile. So that's the which means that the most wave that occurs the most are still under the operational conditions. So moving on to my model development. So since we don't have long-term measure data, so we developed the models to produce continuous long-term data set for detailed resource assessment. So this model based on open source software called SWAN and also use freely available data. So this work also has been published, and therefore the paper should be an intrinsic guide to other researchers or professionals that seek nested local wave model development using SWAN, which is freely available. Bit on my methodology of the model development. So these are the cost model domain. So the important thing here is the model input. So we use FNOC WaveWatch tree at the open boundary conditions here, and then for model domains at the cost resolution we use eTOFO data. For the surface boundary condition, which is wind that drives the wave into model, so we use ECMWF wind data at 0.5 degree resolution 6-hourly interval. So with that, we simulate the models and then calibrate the model for 1 month, and then with the final model setup that we calibrated, then we provide nested boundary conditions for 2 high resolution models at MAT and also Galway Bay that covers west wave as well. With this, then the model domain now becomes 300 meter resolutions with the higher bathymeter data from Informa, and then also using the high resolution wind data as well. Just on the model validation, so based on the result, it shows that the parameterized spectral form compared to the full directional spectra, they are not adversely affected. And with our model as well, we can see that the model improved compared to the previous study. So at M4, which is the location that close to the MS, it shows that our model have lower bias and higher correlation compared to the previous model. Since the model now improve at cost resolution, so it then also improve at MS, which now compared to the previous study, you can see that our bias is lower. Higher correlations compared to the other 2 models that has also used for the resource assessment in the previous study. So then it's justified that the model are suitable for use in the detailed resource assessment. For the detailed resource assessment, I conducted the resource assessment at MS, Galway Bay and Westway. So this also has been published in Energies and also Renewable Energy. So the assessment that we provided are more comprehensive compared to the previous study, where it involved not only power, it also involved significant wave height and also wave energy wave period. And also it's more detailed in terms of specials and special analysis as well as interannual and also seasonal analysis. Again, we have longer model validation period compared to the previous study, and also include the wave characterizations that we developed in the first slide. And with that, we simulated the model for 12 years, and then we provided the resource assessment. This is an example for 12 years annual mean power at cost resolutions, and also at MX and Galway. So from the plots, we can from the figures, we can see that more exposed area have higher resource compared to the sheltered bay in Galway. Just by looking into the power in terms of operational, extreme, and occurrence, so the table shows the 12 years period analysis at berth A, berth B, which is Emmet, and then also Galway and Westway. So since berth A was the outer location, was located at the outer location, so it shows higher resource compared to the sheltered bay. And as expected, winter always show highest resource compared to the summer. And also, now we provide the occurrence based on wave height and energy wave period, since we managed to simulate the energy wave period. So for this plot here, the color scale shows energy, while the numbers shows the wave occurrence. And you can see that, I don't know if you can see, but hopefully you can see, so the highest occurrence does not actually fall under the highest energy, but however, it still falls under the operational condition. So these mismatch are important for developers to tune their device in terms of the C states that they are required to look at. That is at berth A. So also similar pattern shows at Galway as well. And I also looking into the joint occurrence of wave height, wave period, and mean wave direction. So with these informations are important for the device that are actually sensitive to mean wave direction, for example, sea power and also wavecat. So these are important for those devices that are actually sensitive to directions in terms of capturing the power. Okay, so and the last part in terms of the resource stackability is actually looking into the scale between test site. So this work is to investigate either Galway test site is quarter scale compared to the exposed site or not. So with this, we we developed a scaling analysis methodology to appropriately upscale wave conditions at Galway Bay to MX first, and then with that we apply the methodology to Westway. There are three scaling methods that we introduce here. So the first one is crude scaling based on mean ratio. Second one is the distribution fittings, and then the last one is crude scaling based on the assumptions of a quad-scale design. And based on our analysis, it shows that distribution fittings shows the best method compared to the other two. So this is based on the wave height analysis. So the black color shows distribution fitting, blue is fruit mean, and then red is the fruit mean based on quality assumption. So these are the 45-degree lines, so you can see that the closer to the 45-degree means is they came from the same distributions. So as a result, we can say that wave conditions at Galway Bay, they are not quarter-scale proportionate to MS and West wave. Also based on the previous study from Cahill, it's not representative because he only considered the assumption of quarter-scale, and also the analysis was simulated for just 1 year period, which was in 2010, that shows lower energy compared to the other years. So the table shows scaling factors between MS and Galway Bay. So for example, here if a developer wants to look at the annual performance of at MS compared to annual performance at Galway Bay, so the scale should be 1/3.6, which is 2/10. No, is it 2/10? 2/7. Yeah. Okay. And then so if it's winter, then so for example, if they're looking at the test during winter time, but want to look at into the annual performance during the annual performance, then the scale should be 1/2.8. And also same for the others. So basically, we provide different windows in terms of annual and also in terms of seasonal. So you can go into like winter, you can scale from winter to winter, also maybe spring to winter, depending on the window period that you have for the testing. And lastly, for the WAC array impact at Westwave. So this work was done to investigate the WAC array impact on the nearshore wave climate. So the scope of this project is combinations of far-field model using SWAN and also near-field CFD models, which is simulated by Dr. William Finnegan there. And also this is an alternative approach of simulating basic array. So the final, we have 3 final scenarios using 12 devices in a single row, in 2 rows, and also in 3 rows. And these are examples of 12 WACs in 2 rows. With that, we simulated the models, and then based on our analysis, it shows that the percentage difference of wave height was less than 0.1, and also for power, it's less than 0.2 at nearshore area, which is approximately 100 to 300 meters from shoreline, and the water depth there are below 10 meters. And for the depth between 20 to 60, which is 1 to 3 kilometers from shoreline, they are less than 1%, which is all for all cases. And then it shows that it's not significant based on very small reductions in wave height and also wave power. And these are the reductions for first row. 12 WACs in 1 row, and then 12 WACs for 2 rows, and 12 WACs in 3 rows. And also the proposed locations that we proposed in our study meet the distance from shore, which is further than 5 kilometers. And also based on this very minor change, it's expected to have very small obstruction impacts to coastal morphologies. But again, this maybe has to be further evaluated in coastal morphological models. As a conclusions, so the numerical modeling, in terms of numerical modeling, the work has been successful to nested the cost to a local model using SWAN, and then also the model provide accurate model at regional and also at local scale as well compared to the previous study. In terms of resource assessment, the characterizations methodology was developed, which is involved operational and extreme condition. And also our resource assessment involved very comprehensive assessment in terms of wave height, wave power, and also wave period, including wave duration as well. And then the analysis was conducted for interannual and seasonal analysis. Scaling factors, the appropriate scaling methodology was developed, which is the best method was using distribution fitting. But in terms of practicality in industrial standards, so we recommended to use fruit scaling based on mean ratio. As for array impact, the methodology of combining CFD and SWAN was implemented at Westwave, and overall the impacts to the coastline was minor, and then it's negligible. And with that, I will end with the publications that has been published so far with this work. So you can look into more details in terms of the characterization methodology in this paper here in Ocean Engineering. For the model development, it's in the journal, Operation Journal. And for MAT resource assessment in energies, and also we just published this Galway Bay test site, a detailed assessment, and also for resource scalability in renewable energy, and hopefully the 5th one will be coming up soon. So thank you for all the acknowledgements.
Ray wants a video played while we're setting up.
This is wave models with the calibrations. You can see that. This is at M6 here, and that's Galway model at Westwave, Galway and Westwave, and then that is MH at bus A and bus B. So red is model, black is measured. So this line is during the 1 hour interval. So see that.
Good evening, everyone. My name is Anna. Today I'm going to talk a little bit about my PhD research. My presentation is titled Development of a Tidal Flow Model for Optimization of Tidal Turbine Arrays. So this is an overview of my presentation. I'm going to start with an introduction to my research area, to talk about my three main sections, which are resource assessment, tidal energy extraction, turbine array optimisation, and finish up with some key conclusions from my research. Tidal stream energy is a highly attractive renewable energy source. However, tidal turbine technology is still in its infancy. Its commercial viability will involve hundreds of turbines deployed in large-scale arrays. While the associated hydroenvironmental impacts of single-scale deployment are relatively well understood, to date little research has been carried out to investigate the significance of the associated impacts of large-scale deployments. The aim of my research is to develop a hydrodynamic model for optimising tidal turbine arrays, to maximise energy capture and minimise adverse hydroenvironmental impacts. So to achieve this, I had a number of objectives. The first was to develop a methodology to accurately quantify the power available for extraction. The second was to develop the model to accurately simulate and quantify extracted energy. And the third was the development of my optimisation model. The fully developed model is applied to a number of idealised domains, as well as my case study site, which is the Shannon Estuary. The models used in my research were DIVAS, which is a two-dimensional hydrodynamic and solute transport model, and the MSN multi-scale nested model, which has been previously developed from DIVAST. There are three main novel aspects to my work. The first is the development of my optimisation model. To my knowledge, this is the first automated optimisation model developed at SRM scale level, and it's also the first to try and relate the level of energy extraction to the associated hydrodynamic impacts. The second is the development of a localised thrust approach, through which tidal energy can be accurately simulated in numerical models based on the momentum sink approach. And the third is the full resource assessment of the Shannon Estuary, which includes identification of potential turbine deployment sites. My resource assessment study. Traditional approaches to resource assessment, such as the Frankel formula and time-varying total velocity approach, employ the total velocity in their power equation. My research is based on horizontal axis turbines, whose fixed orientation means they can't rotate into the tidal stream as it changes direction during different stages of the tide. This leads to inaccuracy in the total velocity vector in the resource assessment. A methodology has therefore been developed which incorporates tidal harmonic analysis and tidal ellipse theory to identify the prevailing direction of current flow. The mean available power is then calculated using only the time-varying velocity components aligned with its primary flow direction. The three different methodologies are applied to the Shannon Estuary model. The Shannon Estuary was selected as a case study site because it has been identified by Sustainable Energy Ireland as a potential turbine deployment site. The model has been validated against measured water elevations at locations T1 to T6 and against measured current velocities at C1 and C2, and good calibration has been found at all sites. Contour maps of the available power have been created based on the three different methodologies. All three assessments indicated greatest potential to be found in three main areas. This is to be expected as these are areas in the estuary in which the estuary narrows. However, there are substantial differences between the different power estimates. As previously discussed, the developed approach uses the primary direction of current flow to determine the resource assessment. This resource map is then used along with the ellipse ratio of the dominant M2 tidal constituents to determine optimum turbine deployment sites. The criteria for this was areas of rectilinear flow where the ellipse ratio was less than 0.2 and areas where the mean available power exceeded 350 watts per metre squared. And this criteria is user specified. For a further assessment, a number of sites within the estuary were selected. Initially, locations A to F were selected within the three areas of high tidal resource, and they also consider shipping into the estuary. Locations H, I, and J were selected as sites of maximum power, determined using the Frankel formula, and locations G, I, and J were selected as sites of maximum resource, determined using the developed approach. For a further comparison of the three methodologies, the average annual available power at each of these sites was calculated. The Frankel formula was found to overpredict the tidal resource at each of the locations. Comparing then the time-varying total and time-varying primary direction approaches, resource estimates were found to be relatively similar in locations where flow is rectilinear, for example location E. And if we look at the tidal current ellipse of location E, you can see that flow is primarily travelling in one direction. This is further demonstrated when you look at the frequency of occurrence of different power ranges computed using the different approaches. And again, you can see similarities in the results. Substantial differences between the resource estimates were found for locations where flow is more rotary, for example location H. This is one of the sites that fell outside the optimum turbine deployment locations identified during this research. Overall results conclude that resource assessments based on horizontal axis turbines, incorporating the primary direction of current flow, will result in a more sophisticated resource methodology. The tidal energy extraction. Tidal turbines are simulated in numerical models based on the momentum sink approach, in which the turbine thrust is incorporated as a negative term in the governing momentum equations. Turbine thrust is calculated based on the thrust coefficient, which is theoretically defined based on the free stream velocity found upstream of the turbine, here at location 1. However, a numerical model of this velocity is generally taken to be the turbine velocity at location 2. This can lead to inaccuracies as the turbine velocity can be much reduced from the free stream velocity. Therefore, a localized thrust approach has been developed which calculates the turbine thrust based on a localized turbine thrust coefficient, C-T, which is determined based on the turbine velocity. The power extracted by each turbine can then be calculated using this localized turbine thrust. Initial assessment was carried out to assess the sensitivity of the modelled extracted power to specification of the C-T value. The model was run with C-Ts ranging from typical values of 0.8 up to values of 3.0. The suitability of the selected value was assessed by comparing the extracted model power to the theoretical power, assuming a turbine efficiency of 40%. From the results you can see using a C-T value of 0.8, which is shown here by the yellow line, results in lower levels of power than the desired theoretical power. For this particular model setup, a more suitable value was found to be 1.3. Further assessment involved identifying suitable C-T values for different model setups. For this assessment, 40 model scenarios were run, with grid spacings ranging from 16 to 100 metres, and water depths ranging from 30 to 100 metres. Suitable C-T values were identified, and from the results, a C-T specification chart was created, from which suitable values could be identified for any model setup that falls within the range. Results have shown that accurate simulation of tidal energy extraction is highly sensitive to specification of C-T value. The localized thrust approach was then applied to a nested model of the Shannon estuary. 2 levels of nesting were used at a 3:1 nesting ratio, which resulted in grid resolutions of 189, 63 and 21 metres. 4 16-metre diameter turbines were deployed in locations of different depths. This resulted in 12 different blockage ratio scenarios. For the purpose of this presentation, I'm just going to focus on deployment of turbine 1 at the finest grid resolution in the NG 21-metre model. The appropriate C-T value for this model setup was identified to be 1.51, and you can see the model's extracted power matches up with the theoretical, again assuming a turbine efficiency of 40%. The model was also run using a typical C-T value of 1.0, and again you can see lower levels of extracted power. The results have shown the suitability of using the C-T specification chart to identify suitable values. They've also shown the inaccuracies involved in assuming a constant C-T value of around 1.0 for any model setup. The successful application to the Shannon estuary model has showed this localized thrust approach's applicability to realistic tidal environments. My turbine array optimization. The energy that can be captured from a turbine array, as well as the associated hydroenvironmental impacts, will depend on the array configuration. The optimization model aims to position turbines to initially maximize energy capture, and then to implement an impact constraint which will aim to reduce the impacts on current velocities. The optimization algorithm is iterative, so it initially finds the location of maximum power based on a no turbine scenario. This is demonstrated here by the blue circle, and the first turbine is placed. If the impact constraint check is included, this is checked. If it's passed, a new resource assessment is carried out, a new location of maximum power is found, and the second turbine is deployed. If the impact constraint check is not met, this turbine is taken out and replaced in the next location of maximum power. This process repeats until a user-specified number of turbines have been suitably deployed. There are also a number of user-specified constraints within the model. The first is the turbine deployment site. The second is lateral and longitudinal turbine spacings, and the third is the minimum water depth. and they are read into the model from an input data file. The optimization model was initially applied to an idealized domain. A number of different optimized scenarios were run using different spacings between adjacent turbines, and the results were compared to that of an inline array. The performance of the arrays was assessed using the undisturbed turbine efficiency. Looking then at the inline array, you can see the velocity deficits increase as turbines are placed in the downstream wake of upstream turbines. This is due to the cumulative wake effects of the placement of turbines. This then leads to a reduction in performance of the individual turbines and of the overall array. Looking then at the optimized arrays, considering initially only maximizing energy capture, the optimized configuration is defensive turbines. This is to be expected as no turbines are placed in the downstream wake of upstream turbines. Comparing the performance of this optimized array to the inline array, you can see the optimized configuration reaches a desired turbine efficiency of 0.4, which is substantially higher than the 0.3 efficiency determined from the inline array. When the impact constraint is applied, 2 turbines are removed from the fence formation and placed further downstream. This leads to a reduction in the impact on velocities as it breaks up the wake merging that occurs in the fence formation. Again, the performance of this optimized array is high, with a turbine efficiency of 0.3. The optimization model was then applied to the nested model of the Shannon estuary that I previously discussed. The turbine diameter was increased to 21 metres to match the grid resolution of the finest nested grid. Again, optimized arrays showed improved performance from the inline configuration. If we look at arrays deployed in the NG21 grid, you can see the turbine efficiency for the inline array reaches only 0.1. For the optimized array, considering only power, the turbine efficiency is substantially higher at 0.33. A key finding from this assessment is the importance of grid resolution when determining your optimized arrays. As you can see, the optimized configurations are substantially different across the different grids. This is because at lower resolutions, more than one turbine can be deployed in a single grid cell. There are also small changes in the velocities computed across the different grids. Since power is proportional to velocity cubed, this can lead to substantial differences in the locations of maximum power, hence leading to differences in the array configurations. Overall, for this assessment, it can be concluded that the NG21 meter model developed at turbine resolution will be the most accurate, as it can actually capture interactions between the turbines and the turbine wakes. Some of the key conclusions then. The resource assessment methodology has been accurately incorporated into the hydrodynamic model. Results have shown that for resource assessment based on horizontal axis turbines, considering the primary direction of current flow will lead to a more sophisticated resource assessment. The localized thrust approach has been accurately incorporated into the energy extraction model. Results have shown the simulation of tidal energy extraction based on momentum sink approaches are highly sensitive to C-T's resource specification. The optimization model has shown to be accurate, to be correct in positioning turbines to maximize energy capture and to minimize impact on current velocities. In all cases, the optimized arrays were found to have improved performance from the inline configurations. The developed model has been shown to be able to be applied to any tidal environment at any grid resolution, and can therefore provide a very valuable tool for turbine developers and tidal energy researchers alike. So I'd like to thank the Irish Research Council and MaREI for funding my research, and thank you for listening.
Yeah, so I'm Ed Fagan. My PhD project was on designing blades and designing using optimization tools, kind of developing automated optimization of the structural kind of aspects of wind turbine blades and also tidal turbine blades. For a bit of background, so Anna already provided background on the kind of development of the tidal energy industry. An example I've shown here on your left is a picture of the Scott Renewables, their SR2000 with their 2 megawatt turbine. So tidal energy is a relatively new kind of form of renewable energy, but they're really starting to scale up and get to the commercialization level now. Most of the tidal devices out there being developed are focused on this horizontal axis device. So some of you might be familiar with Open Hydro. They're an Irish company, or Irish originally, and they're developing very different. They're an open-centric turbine, but for the focus of my own research, I kind of stuck with the most common or most kind of popular type of tidal turbine device. And then a picture on the right is a picture of some tidal turbine blade testing. So like in the wind turbine industry, the full-scale structures for certification reasons and for comparisons to your finite element models and for reasons of design need to be tested. Now they're not tested in the water for the most part. Structural testing happens in the dry, and you use either hydraulic actuators or cranes and winches, and you load up your blades in a method that is comparable to the operational loading that you experience, operational or fatigue. Here at NUI Galway, let me actually go to full screen here, so. No. There we go. Thank you. Alright, that's better. So here at NUI Galway, we have this is the mock-up now, or a CAD model of our test facility in the Heavy Structures Lab. So we have steel reaction frames sitting on a concrete strong floor. How we load up our blades is using 3 hydraulic actuators that are run off the ring main. So they vary from 250 up to 750 kilonewtons overall load. So we can tie those 3 together and basically apply a distribution of loading across the blade that's representative of the operational loads. Or if we're looking to tie them together and run them in concert, we can actually apply fatigue loading. So, as part of the project, I decided to develop a design methodology. The reason behind this was when you're designing a blade, there's a huge number of variables that can be taken into consideration. So you've got the different materials that you're going to use in your blade construction, you've got the thicknesses of the material in different parts of the blade, you've got the blade shape. So there's just a whole huge design space encompassed by all these different variables. When it comes to making and testing them, really the way things have moved, especially in engineering in general, is to move to computational design. So using finite element programs, Abacus in this case, I wanted to automate that entire design process into a single methodology or a single code, really. So the main, I guess, drivers behind why I created the methodology were 1, automate where possible. 2, incorporate physical constraints. So I want to make sure that our blade designs and how we generate the models is representative of real life. In tune with that, you use well-founded assessment criteria. So when we're assessing our blades virtually, we're looking at strength, stiffness, deflection, etc. And then to take it full circle, we want to come back and compare a physical blade that's been manufactured based off of our design optimization and use experimental testing to kind of corroborate what our optimization code has given us. So I suppose those 4 points taken and put into the blade design methodology are kind of shown here at the bottom. The methodology's got five main components to it. So 1 are the finite element structural models, the ones I mentioned there, that's Abacus. You can kind of see a picture on the left. Incorporated into that then, we bring in damage models for static failure and fatigue failure. So they're based off of composite materials damage modeling that's available from the literature. And then to incorporate as well realistic loading using, in this case, BMT analysis, which I'll talk about a little bit later on. And then to really tie it all together using genetic algorithms to search through all those different design variables and optimize it. And then just shown on the right as well as an example of some structural testing of smaller scale 5-meter wind turbine blades. I'll kind of get to that. That's in the validation side of the project. On finite element modeling, I kind of talked about the different variables that are available to us. In the examples I looked at in the project, on wind turbine blades especially, the outer profile, so the shape of the blade was predefined. So we had 2 different types of blades that we tested, and what I was able to do then was look at just optimizing the laminates, so the thickness of the materials, the plies and the spar caps and the shear webs or in the outer profiles, and looking at where those thicknesses change along the length of the blade. So the kind of 4 red planes define the places where the plies drop off, where you get distinct drops in thickness along the length of the blade. Then, I suppose I'll explain a little bit of what genetic algorithms really are. When you're using genetic algorithms, you're really, in a computational context, you're using the concepts of like evolution or natural selection. So at the very start, we create a population of just random blade designs. So like I showed here on the left, the thickness of all the different variables or all the different sections throughout the blade are randomly generated. Then, within the FE model, we evaluate the fitness. So that means we either assess it for the stresses in the different parts of the blade, or the overall stiffness or the mass if we're trying to optimize and reduce the mass of our blades. So then, each of our blades basically has a fitness value or an objective function. Moving on from that, then we take the best ones, the best blades we've assessed, and we reproduce them. So we cross over or mutate the different designs. So certain characteristics like the thickness of, say, the spar caps in one blade might be applied in concert with some of the characteristics from another blade, and then we'll have some random mutation as well as those design variables. That gives us a whole new population, which is assessed, and the process then repeats for however many generations. And then, ideally, at the very end, you end up with an optimum blade design that you might have come across or come to out of your own sort of intuition, and so you get quite non-intuitive designs resulting from genetic algorithms. On the wind turbine side, so I suppose in some background to the project, we had two different scales of wind turbine blade that we were able to test. The first one here were blades that were 13 meters long. The initial part of this project involved basically modeling the blades and analyzing their performance compared to just the deflection and mass data. So we got quite good correlation just on, I just showed one of the static tests on the right for the 13-meter blade. So moving on from that, after we'd calibrated our models, I looked at varying the thickness of all those different laminates, and you can see on the bottom left, the reference blade, the one that was tested, is shown in grey, and then the optimum blade that came out of the genetic algorithm is shown to have similar thickness laminates towards the root, where the stresses are high, but a significant reduction in the thickness of the laminates out towards the tip. And while we're doing that, we're also assessing the risk of failure or the stresses due to the stresses in the outer part of the blade, and we're able to keep within limits set by design factors. I suppose just the fitness function on the right, or the plot on the right shows the fitness of the entire population. So of all of our, I want to say 25 blades that were assessed with each generation, you see a lot of variation in the fitness towards the 150 to 200 generations. So those, at that number of generations, you've basically gotten to kind of a single optimum blade, but the random mutations introduce a lot of scatter. That's actually really good for the analysis, because we can keep our best blade the whole way through, and that mutation might get us to a slightly better blade that just the other crossover processes wouldn't get us to. So following up from that, I tested some 4.5 meter long blades, and our setup is shown here on the left. Got a whiffle tree, which maybe it's the clearest there. The whiffle tree spreads the load along the blade at 8 separate loading points, and they're designed to represent the operational loading on the turbine. And I had set it up with a 3D laser scanner, as well as string pots or linear LVDTs, string pots, strain gauges, load cells, etc. So I was able to pull out the strain along the blades as well as the deflection, and then compare them back to validate our finite element models. Looking at, so I should say the optimization process, the same one I described for the 13-meter blade, was applied for these 4.5 meter long blades, and the resulting blade design was then manufactured. And so this shows some of the test results of the newly manufactured blade. So the laser scan results are compared to the FE on the left, and there's some comparison between the deflection data in X, Y, and Z direction, a number of places along the blade. The new optimum generated blade was slightly stiffer, or showed slightly lower tip deflection, I think it's 15%, than the original glass fibre blade, also for a drop in overall mass. So you can see some, out of the optimization, we're seeing a reduction in material costs as well as an improvement in overall stiffness. So after the whole process had sort of been validated against wind turbine blade models, moved on to the design of tidal turbine blades, and first looked at the static failure. So the FE models were set up to incorporate just basic uniform steady loading on a blade, and the submodeling techniques were used to just look at in a little more detail at a specific section of the blade. So here on the right, the high stress region of the blade is pulled out in the modeling process, and a computational damage mechanics code based on puck failure criteria is applied. So if people aren't familiar with composites, the puck failure model is phenomenologically based, and it's used for determining the risk of failure for fibre failure or different forms of matrix cracking in composites. And submodeling lets us just look at the really highly stressed regions of the blade in a lot more detail and determine if there's any degradation of those plies. As well as that, the automated methodology allows you to look at a number of different load cases. So I've just shown here on the left the strain in the outer plies along the blade for a number of the different load cases, and then you can iterate through all your different designs to get lower than predefined safety limits. And the damage model shows us regions of the blade that are at risk of degradation under extreme loads. So that's all kind of incorporated into the methodology. Moving on to fatigue, then I've shown a tidal turbine blade here, or tidal turbine here on the left. So I looked at two specific forms of fatigue that tidal turbines will be susceptible to. So the first is the tidal shear profile. It's just shown here as a 1/7 power law. So we got actual tidal current and magnitude and direction data from a location in Scotland, just near the Orkney Islands. So from the month of data, I was able to pull out the loads pull out the operating conditions for a turbine operating over the course of the lunar cycle, as well as that shear profile through the water depth. Then again, for people familiar with composites, used Miner's rule and rainfall counting. So based off of the constant life diagrams, or shown here the constant life diagrams for two different forms of glass fibre material, and bring that into methodology, it allows you to look at the certain risk or areas in the blade that have risk of fatigue damage, and we're able to pull out the number of cycles, the stress range and the stress mean in different regions of the blade that might be susceptible to damage. So I won't go on much longer. I suppose the final remarks are just that what's been developed is an overall methodology that incorporates static and fatigue design of different types of blades. It also incorporates physical testing that was used to calibrate the models, so both on the wind turbine side, and then the whole methodology has been demonstrated through from design through optimization and to manufacture and testing with the 4.5 meter wind turbine blades. And yeah, I'll leave it there. Questions?
Okay, so a range of talks is what's going from the waves offshore to nearshore and into the tidal estuary side of things, and looking at tidal arrays right the way down to designing one of the elements of a tidal device, being a blade, but also how that's applied to a wind turbine as well. So a pretty broad range of topics, but all coming under Marine Renewable Energy. So I'll open up the floor to questions or comments.
Very nice talk, all of you actually. Just a question for you, Reduan. For the type of wave profile that you're seeing for the Galway Bay, have you looked at, is the market well served with devices that are suitable for that kind of amplitude of waves or magnitudes of waves, or are we going to see more of these devices in Galway, do you think?
I think if you, like, for example, for commercializations, you might not want to deploy the device in Galway because it's a very sheltered area, so mostly they are for testing. And for Galway Bay itself, so the range of the wave, it's from maybe 1 to maximum 4 meter wave height. So that's not actually for the bigger device. So for example, that's the reason why they're actually doing Galway Bay just for testing. But in terms of production itself, you can still produce electricity or energy based on the specific device by looking at the range of the wave height mainly, or wave period. But yeah, it's really depending on the device. Normally smaller device in Galway Bay. But if you want to do more commercialized, then firstly is you bring the device to Galway Bay for the test, and then after that you try to bring it to the MS, which is the full-scale test site, and then for the demonstrations, then you bring it to the West Wave. So that's why we actually recommended all those scalings, different test sites. But the range there varies. You can choose different devices of different type of wave.
So it's an intermediate between your lab scale and your full scale before you're ready to go into open water. It's in between there. So you're calling it a quality scale test site, but it's not quite. You can see there from his results. So I think it's 2/7 or something like that of a scale annually. But if you only have a winter window in Galway Bay, then from his work you can say, okay, if I winter in Galway Bay, what scale should I look to put in if I want to get an equivalent full-scale device up in Balmullet or off Clare in the West Wave site? Or if you're looking at extreme conditions in every winter in Galway Bay, what size device would you need there to be equivalent to extreme conditions in Balmullet or in so that would be a different scale device. And that's based on 12 years data?
12 years,
to Reduan. My question was related with the scales and how they work for different seasons of the year.
Oh yeah. So basically we have the full table that's covered the whole seasonal period. So basically, if you want to scale your device or test your device during the annual, you want to look at the annual performance. But like Jamie said, you only have window to test, so you want to scale it based on the annual winter performance. But if you want to scale during winter periods against winter period, then we choose different numbers based on the table that we have. So we have all different seasonals and annual as well for all different types of scaling factors, and at berth A, berth B, also at West Wave as well. So this is just example at berth A. So we have more. So for example, when I say winter, so we have winter and winter, which is this number here that you use. So for example, if you only have summer window, but you want to look at into that, say, autumn in Galway, then you have to use this one here to scale. So you can all look in, depending on which window periods that you have at those test sites. So, and that's
it's very obvious between things if your test period is winter, maybe 1/2.8 would be the scale that you put in Galway Bay if you wanted to look at your final deployment of berth A in Balmullet. Whereas if it was a summer window that you had in Galway Bay for testing, then you would look at your device with 1/4.7.
Which is 2/5. So
2/5 over, and then if you're going to live in Galway Bay for the full year, that would be equivalent to 1/3.6, which is 2/7. Or then you might be looking at extreme conditions, and so if you're most interested in extreme rather than the operation, then you might want to have a different scaling in there. So if you want to scale winter to winter, it would be more like the same as the annual, very similar to winter to winter or spring to spring. You see the scaling for the significant wave height based on the broad scaling. They're very similar numbers for the period as well. So the recommendation that Reduan has is to just use this table for scaling, because you can see the numbers are almost equivalent for the period as they are for the significant wave height. Any other questions or comments? Yeah.
Just Edward,
Sorry, can you just introduce yourself as well?
apologies,
Sorry,
James Lee, Subsea Software. I was interested in the optimization techniques you're using there. And I was just wondering, did you consider using structured reliability analysis numerical in place of the optimization? And if you did, why did you go for the method you choose?
Yeah, I suppose I went for genetic algorithms initially. I'd looked at a couple of different options. There's kind of gradient-based optimization and other ones. Genetic algorithms seemed well suited for the problem we were looking at. I'm not familiar. What was the one you used?
Structural reliability analysis, probability theory.
Oh, okay.
Run quite a lot of analysis.
Yeah, no, again, so one of the nice things with genetic algorithms was quite a number of analyses do have to be run off, but you quite quickly kind of get to, I don't know if I put up any plots of the different, or of all the results, but no, I don't think there's one there. Oh yeah, maybe there. So you quite quickly get very close to your optimum, so only in maybe 50 generations, and that's, there's maybe a minute or 2 minutes on each analysis run, between like pre-processing, post-processing, and analysis itself. So genetic algorithms kind of worked out at a nice kind of midway point between computational costs and actual, and then the results we're getting out of it. So I suppose potentially if the actual cost of running a single analysis was much lower, that might be a good alternative. I'd probably, since I have the model set up at this point, I'd be more inclined to just kind of increase the design space and just run through a whole different bunch now. But yeah, there are a lot of different optimization kind of routes out there, and there's different sort of flavors one person prefers over another. But yeah, I found it quite useful.
Yeah. Thanks.
Any other questions?
For Ed, you mentioned that at the end, the final design you got had some characteristics that might not be, you might not think about that in the beginning.
Yeah.
And I remember you mentioned one characteristic related with the stiffness.
Yeah.
That was stiff more in some parts more than you expected.
Yeah. So I suppose.
What do you think of that?
I suppose the overall results we got, a stiffer blade and a lighter blade, were as we'd expected. That's kind of what our objective was within the analysis. The design, the variables itself, so the thickness of the regions in different parts of the blade mightn't have been as intuitive as you might have expected if you're just going from kind of first principles analysis. So I suppose I did a different multi-objective analyses for a few different types of blades, different wind turbine blades and different tidal ones, and when we were looking at a single objective like here, where we were just optimizing to reduce the mass, the actual design came out as you'd expected. It made a lot of the laminates throughout the blade thinner, the ones that were less structurally kind of maybe important for the fitness function. But when we were optimizing conflicting variables, so optimizing the mass, but also optimizing the strength or the stiffness, then you were getting certain parts of the blade that you mightn't have expected ended up being, say, thicker than you would have expected, I guess. So, I mean, I had kind of a couple of papers out on this, and the papers go into a little more detail of discussion on how the design variables are set up and then the results of them afterwards. But yeah, we could chat about it after.
Any more?
Ed, I'll just ask you another question. So when you were defining the range for each of those parameters,
yeah,
did you find at the end that any of those optimum values were, at the kind of bottomed out or maxed out?
Yeah.
In line with the limits that you said, and did that?
Yeah, that
cause you to redefine limits, or
that did. Yeah, that came up. So again, I suppose in this example, really, where we're just minimizing the mass. That did happen. It kind of just bottomed. It went to the lower limit for, say, some of the shell laminates that aren't structurally that important for the stiffness that was being assessed. In the cases where we conflicting variables, that didn't really happen. You had some laminates that maybe went to the lower limit, but for the majority were kind of sort of a mix of anywhere between those upper and lower limits. So I suppose for the more complex analysis, the multi-objective ones, that wasn't really an issue. But for the ones where we're just minimizing or maximizing a single variable, then the upper and lower bounds did have an effect, yeah.
So that changed how some parts of these blades are made, do you think? Is that going to impact on
I'm working on a postdoc now where we're designing a blade for Scott Renewables, because I showed at the start. And when it comes to the manufacturing, there are certain manufacturing limitations for, say, like you're not going to have 300-400 millimeter thick laminates even at, say, the root of these blades. So there's physical upper limits to certain design variables that will be incorporated in it, and say even kind of lower levels that you don't want the thickness of your outer shells going below a lower limit for, say, if there was buckling issues or risk of buckling in the shear webs or something like that. So when you take the kind of physical constraints into play, you'll find that your upper and lower limits kind of become well enough defined. I suppose so that it's all kind of in the problem or the design of the problem start.
You did redesign the blade, like one of the wind turbine blades using this algorithm, and it did come out, that's the results in that bottom right one, that they made his optimum blade and tested, and it came out to be a lighter blade and performed according to the specification of that. So we'll see if that's going to be the standard blade in the future. I'm not sure.
But if you tested it and it passed the requirements, they built the redesigned blade, why wouldn't they adopt it?
The short answer, I don't think they're making those blades anymore. So,
I guess so. To extend it then, just a quick question. It seems like it's very useful from a commercial point of view. Not knowing what the reference blade was, but have you tried to look at, there's not so many blades in that segment of the market, most of them are all 40 meters plus.
Yeah.
Have you thought about doing it for that range?
Yeah, definitely. So I suppose the next scale that we're looking at with the tidal turbine blades, we're looking at something that is operational and that is kind of a growing market. On the side, these I kind of have the analysis set up and ready to go now, so I will be running off planning to look at different kind of scaling effects. So once we do get up to those 40-50 meter blades, where the different materials become optimum. So I suppose the next step is to go for a little more kind of nuanced objective function where you're looking not just at, say, the mass of the blade, but also the overall cost of manufacture if you take into account changing the materials or changing the processes that are behind the use of each material. So like the basic optimization is ready to go. It's just coming up with your objectives. It's kind of an interesting field. I think there's a lot of kind of scope for development out there.
Is it quasi-isotropic in the shell?
In which?
And the shell material and the shear webs?
Yeah, so for the tidal blades, they're it's UD spar caps and then quasi-isotropic everywhere else. I think the shear webs are probably biaxial, just plus or minus 45s.
And then at the root and stuff, like in reality, because I don't know much about it, in reality, do you use it kind of you come up with an optimized design or something, but then in reality you might have to change some or something to suit the design itself.
Yeah, exactly.
To take into account some other factors.
So we saw that with even just the 4.5 meter blades. When it came to manufacture, the width of the spar cap itself, so the kind of unidirectional plies that stiffen it, was it worked within the model, but when it came to manufacture, the actual bulk thickness of the plies before they had to go into the mold was a good bit higher than expected. So we had to basically kind of modify them, trim back that shear web, or not the shear, the spar cap. So like you can see the orange at the top, the FE model compared to the actual test blade. Like I suppose the Y direction or the delta 1 deflection was a good bit lower in the FE model. That was due to the manufacturing constraints that had to be applied later. So like it kind of reduced the stiffness. The next I suppose the next development for that set of modelling will be to incorporate that constraint into the actual design setup of the genetic algorithm.
Brian Finnegan, anyway, Galway, your composites. Aaron, can I ask you a question about, you talked about modelling in the Shannon estuary, and you mentioned you took shipping lanes into account in your model. Was there many areas then left when you took shipping lanes out of it that you could place these tidal turbine blades, or are the results what you showed where you could place them? And as the tidal energy market it's kind of taken off now, where we can see something like what Ed's doing on the Scott Renewables blades hitting full scale. Open Hydro's got some full scale. There's a couple more companies, Siemens. Do you think we're going to see tidal energy in the Shannon in the coming years? Is there enough scope there based on, is there enough sites for it?
I think so. Like, a lot of people are doing work in that site, and like, say, like all them locations, you know, the shipping lane I maybe should have put a map up, but it just kind of ran through like the very centre of it, so it wasn't taken up like a significant proportion of it.
Like, when I think of this Shannon, I just assume it's quite busy and like boats everywhere.
Yeah.
You don't want them running into your devices, but you reckon there's enough there though for everyone, essentially?
Yeah, I suppose that would depend then on like the configuration. Like maybe a big fence of them only run into like practical problems, but if you could like stagger them, you could put them into your, like when you're optimizing it, you could consider them factors.
Okay, so any other last question? Okay.
Okay, well, now it's someone else.
Well, I'll ask them tomorrow. I'll ask again after you, don't worry.
Sorry, for Anna. You were also optimizing the calculation of your thrust coefficient for the power calculation. So you use the theoretical power to identify which is the correct value. In this theoretical power, did you consider the number of turbines?
So yeah, I just put like a specified number. So it was like 12 and 18, I think, then for the Shannon. So that's just user specified. You can decide how much you want to put in.
Okay, so any other last question? No? No. Okay, so just before I thank the speakers, just to acknowledge that this talk this evening is co-hosted by a number of different organisations. So one being the MaREI Centre, where these guys all work. The second one being the College of Engineering and Informatics here in the university. The third being the Ryan Institute, which is the research institute here for the marine, the environment and energy. And then the other being Engineers Ireland West Region as well. So there's a few members of the West Region committee here, so if anybody's interested in getting more involved in the Engineers Ireland West Region and the activities, then you can talk to me or William or Maeve is somewhere. Maeve is there as well afterwards and that. So this is our third talk that we've had in this kind of series over the last 3 months, mainly focused on energy, but more focused on the marine and that. So we're looking, I suppose, to try and continue talks in the energy sphere over the next year, maybe 3 or 4 more other ones anyway, because it's from a survey that was done from Engineers Ireland members, that was, I think, project management seemed to be one of the top things that people were looking for more talks in, and energy was number 2, I think, on that list as well. So if anybody is interested in giving a talk or has ideas for people for talks and so on, then let me know and we'd be happy to host it. So we've actually got the facility here to webcast it as well. So I know that the link was broken at the beginning because I had 3 or 4 or 5 emails there from people asking for the link and that. So just say thank you to all you for coming, to the people online, but in particular to the 3 speakers who obviously have put in effort to over 4 years for their projects, a lot of effort in it, but then to put the slides together and to give the talk to people. Thanks a lot.